A median of a triangle is a line segment with one endpoint on a vertex of the triangle and the other endpoint on the midpoint of the opposite side. Well, here's a triangle, and we'll take a look at this triangle to figure out how the word opposite applies to vertices of a triangle. Well, each vertex is an endpoint of two of the sides, and it is not a part of the third side. It's that third side that we say is the opposite side to the vertex. So in this case, point A is opposite of side BC. Point B is opposite of side AC, and point C is opposite of side AB. So here's our first median. We've connected A to the midpoint of the opposite side, and D is the midpoint of side BC. Here's another median. B is connected to the midpoint of side AC, which is point E, and our final median is CF, because vertex C is connected to the midpoint F of side AB. Notice, all three of these medians come together in a single point. When three or more lines come together at a single point, they are said to be concurrent. Now let's take a look at some other triangles to see if medians are always concurrent or whether this might just be a special case. And in order to take a look at some other triangles, we're going to drag around some of the vertices of our original triangle. And you see as I drag point A, the triangle changes, the lengths of the sides change, but all three medians remain concurrent. So let's drag point C around. Same thing, we'll flip it over on itself. But the medians all seem to be concurrent, and they always seem to come together in the interior of the triangle. Let's take a look at another definition. An altitude of a triangle is a line segment drawn from any vertex of the triangle to the line containing the opposite side so that the segment is perpendicular to that line. An altitude is often called a height. Well, here's an altitude. It's from point A down to the opposite side BC, and it's perpendicular, so we've marked it with the sign for perpendicularity. Here's another altitude, BH. It goes from B to the opposite side AC, and a third altitude, CI. From each vertex, there's an altitude to the opposite side. These altitudes all appear to be concurrent. So once again, we're going to look at some other triangles and their altitudes to see if this is a special case or whether the altitudes of all triangles have a point of concurrence. Here's a triangle with three altitudes already drawn. And again, we're using a favorite piece of software, the Geometer Sketchpad. And we're going to drag some of the vertices around to change the lengths of the sides to see what happens to the altitudes. So far, it looks a lot like the medians. Here's another vertex. And here's our third vertex. But now, look what happens when I make one of the angles a right angle. Two of the altitudes appear to disappear. But in fact, you can probably guess what's happened is they coincide with two of the sides. In fact, those two sides in a right triangle are called the legs. So the legs of the right triangle coincide with the altitudes for two of the vertices of the triangle. Notice this altitude here that goes to the longest side, which is known as the hypotenuse, it's still there. We can see it fine. But now let's drag and make an obtuse angle, and now I don't even know where the altitudes have gone. They have disappeared. But let's go back to the original definition. It stated that an altitude was drawn to be perpendicular to the line containing the opposite side. So we need to extend the sides of these triangles to see the lines that contain these sides. And now we've done that. We've not only extended the three sides of the triangle, which are black dotted lines, we've also extended the altitudes themselves, and the extensions are green dotted lines. So now, when we make a right angle, there you see it. The altitudes coincide with two of the sides, and as we extend, we can now see those altitudes fall on what we call the exterior of the triangle. But when we extend the altitudes, shown here that I'm circling at the bottom left, that's the point of concurrence, but it's outside of the triangle. But here's an altitude. It goes to the side extended. Our altitude to the hypotenuse is still in the interior of the triangle. And over here we have a third altitude, which runs from this point down to this side extended. And so altitudes can run on the outside of a triangle or the exterior of a triangle if the triangle has an obtuse angle. Here's our right triangle again. And now we're looking at a variety of acute triangles. An acute triangle is a triangle where all three angles are acute angles. And now we go back to a right triangle and an obtuse triangle. And here's a definition we've had before, angle bisector. An angle bisector is a ray that divides an angle into two congruent angles. Well, we bring that up now because we're going to find the three angle bisectors of the three angles of our triangle. So ray AJ is an angle bisector of angle A. Ray BK is the bisector of angle B. And ray CL is the bisector of angle C. And notice, once again, all three of our angle bisectors have all come together in a point of concurrence. And once again, we're going to go and move the vertices around to see if that's consistent for all triangles. Here's our angle bisectors. We'll pull this vertex down, get it right in the center of our frame. We can move them around. The one thing about angle bisectors, just as with the medians, the point of concurrence always appears to be in the interior of the triangle. Here's an obtuse triangle. We're going to pull this up and see if we can make a right angle, see if it looks special. Kind of right in the middle. This is pretty close to an equilateral triangle. And you can see that all of our angle bisectors seem to always come together somewhere in the interior of the triangle. And now we're going to do one more thing. We're going to look at the medians, the angle bisectors, and the altitudes all at the same time for our given triangle. And there they are with all our labels. Our medians are blue. Our angle bisectors are red, and our altitudes are green. Let's drag around and see what happens. Well, you can see all the blue ones stay together, have a point of concurrence, so do the red ones, and so do the green ones. But sometimes the green ones, those are the altitudes, have a point of concurrence, which is in the exterior of the triangle. If we work to make our triangle an equilateral triangle, and we're careful, we might be able to get them all to come together. So it appears that if we can get an equilateral triangle, that an altitude, an angle bisector, and a median all coincide for each vertex to its opposite side. And the point of concurrence for all three of these is the same point in the middle of our equilateral triangle. If we make it so that two sides are the same, but one side is different than the other two, an isosceles triangle, we get a little more symmetry, but not as much as we had with the equilateral triangle. And now let's take a look at a right triangle. And there it is. And how about what we call an isosceles right triangle? That brings quite a few things together. And what we're looking at is medians, altitudes, and angle bisectors of a given triangle, and we are sliding things around so that our given triangle keeps changing from one triangle to another. And one more thing for this lesson, auxiliary lines. Sometimes we find it helpful to draw additional lines, rays, or segments in given diagrams. We can do this because of the postulate that states 2 points determine a line, and I'll show one example. We've got a diagram, and we're given that within that diagram, segment AB is congruent to segment AC, segment BT is congruent to segment CD, and we're asked to prove that angle B is congruent to angle C. Well, the first thing we're going to do is mark up based on the given. Then we're going to state the first given, and then the second given. And now here's where our auxiliary line comes in. we're going to draw AD, and we can do that because 2 points determine a segment. And now let's show how we've drawn it. And there it is, the red segment from A to D. And now we have 2 triangles. And each triangle already has 2 pairs of sides proved congruent. And if we state that AD is congruent to itself by the reflexive property, we have 2 triangles where we've shown that all 3 pairs of corresponding sides are congruent. So we can state that the triangles are congruent by side, 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 and therefore angle B is congruent to angle C by corresponding parts of congruent triangles are congruent. In this lesson, we've looked at the definition of a median of a triangle. We've also looked at the definition of an altitude of a triangle, and an altitude of a triangle is often called the height. And we took another look at the definition of angle bisector. And finally, we looked at auxiliary lines. We use auxiliary lines quite a bit, and we can draw auxiliary lines because 2 points determine a line.